All right, I'm going to guide you through this worksheet. I just started it, but we are going to get right to it. So the sheet, reference table, calculator, something to write with. First question, how can you get a real gas to behave the least like an ideal gas? Remembering that an ideal gas has no intermolecular forces. So I drew this, sad little picture here showing a container with a movable piston, and we could get it to behave least like an ideal gas if we give it a very little space. So that would be decrease volume, or we could say it as increase pressure. Okay, and then the other thing we could do is make the particles move very slowly, and we could do that by decreasing the temperature. If we do this, the gas is very, very, very far from ideal because it's squished in a little tiny space. There's tons of pressure on them, so the particles are really close together, and the temperature is low, so they're not moving rapidly as gas particles normally would. All right, on to question 2. Of the following, here's my options, which would behave least like an ideal gas? Okay, well, this will help me a little bit. When will things behave least like an ideal gas? Well, if they are big, so big mass. If they are polar, what else? And then like our situations up here, if they are at low temps or high pressure, low volume. Okay, but this doesn't really say anything about temperature, pressure. It just gives me these substances. Okay, well, this doesn't have any bonds. It's a noble gas. This is nonpolar. This is also nonpolar. So that's not particularly going to help me. So it's probably going to be mass that's going to be the one. So if I look, mass of hydrogen, mass of helium, those are very small. And then if I look, this has 1 carbon and 2 oxygens. And there's the mass of carbon. It's already bigger than these two. So carbon dioxide is going to be the least like an ideal gas. Why? CO2 has the largest mass. And when it has the largest mass, is going to behave least ideally. Okay? Boyle's law relates pressure and volume. So when the pressure is increased on a gas at constant temperature, the volume decreases. Okay, and we show this in a graph like this. It is curved. It is not, so does not look like that. Okay, it is not, because that would imply it would get down to 0. This graph means it's going to get closer and closer and closer, but not quite get there. Okay, so this is Boyle, right? And this is pressure and volume. So this is pressure, and this is volume. Our graph doesn't mean a lot without a key, okay, without some labels. So this is saying as the pressure increases, the volume decreases. All right, pilots suffer from intestinal pain when they fly because at higher altitudes, the pressure is decreased. Remember, we should remember that if here's a column of air, lots and lots and lots and lots and lots of particles down here, and then we get less and less and less as we move up. Okay, so this up here has less air pressure. So the pressure is decreased, so the air volume in their body, what? Well, let's see, if the pressure is decreased, that means it's a little over here, then the volume must be increasing. Okay, so pilots suffer from intestinal pain when they fly because at higher altitudes the pressure is decreased, so the air volume actually increases. So think about it, it's the belly like swollen with too much air in there, okay? The abdomen. Your lungs suck in air when the diaphragm is enlarged. When the diaphragm opens, the lungs expand. The lung expands. The volume, what? And the pressure, what? Which allows air in. Okay, When the diaphragm collapses, there's less room. Okay, so this should be obvious. If there's less room, the volume decreases. If the volume is decreasing, right, the volume being smaller, the pressure has to be increasing. So that means the opposite. So I'll go back. When the diaphragm opens, the lung expands, gets bigger. So that means it gets big. So the volume is increasing. Why is it increasing? Because the pressure must be decreasing, because they are opposite of each other. Okay? So this applies to real life. So although we're talking about it in the context of chemistry, this is literally biology. It's anatomy. Okay? All right, now let's look at the next one. We're going to look at Charles's law. Charles' law relates volume and temperature. Okay? So it says when temperature is increased. So I'm going to put temperature over here, volume over here. When temperature is increased on a gas at constant pressure, the volume what? Well, and it says it's a direct relationship. So it increases. So it looks like this. Okay? Not a graph similar like this, not with that curve like this. No. Okay? So hot air balloons work based on density changes affected by Charles's law. To rise, the temperature is, okay, increased. If you think about it, they turn on the flame. And the volume, so what if they're increasing the temperature? Oh, the volume increases. The balloon inflates. Okay? To make the density lower. To come back down, the fire is turned off, so the temperature decreases. And the volume, well, if the temperature is going down, the volume is also going down, decreases, so that the density increases. The balloon is always inflated, so the pressure is relatively constant, but this allows the balloon to either rise in the air or come back down. So there's Charles's law. So we have Boyle's law, Charles' law, and then we have one more law, Gay-Lussac's law. Gay-Lussac's law relates pressure and temperature. When temperature is increased on a gas at constant volume in a rigid container, what happens to the pressure? Well, it increases. And it says this is a direct relationship. So when we increase temperature, pressure. So like this. Okay? And this is Gay-Lussac's law. Now, interesting to note, although these names may be mentioned in a question on the exam, you are never expected to memorize the name. Like, what was Charles's law? What was Gay-Lussac's law? Okay, you're not going to be asked to memorize that. All right? So now we're going to move on to the back, which has a little bit to finish up Gay-Lussac's law. Drivers need to check the air pressure on their tires during the change of seasons. In the winter, the temperatures decrease, so the pressure inside the tires, what? Well, if the temperature is going down, look here, the temperature is going down, the pressure is also going down. So the pressure is lower, and the tires are flat. In the summer, temperatures are increased, and the pressures are, so again, if you look, as the temperatures go up, the pressure goes up. All right? So these are higher. So the tires are swollen, but the volume the tires air can occupy stays the same. Don't put aerosol spray cans in direct heat or flames because they explode. Explain this phenomenon in terms of pressure and temperature. Okay, so first of all, in an aerosol can, the contents are already under pressure because when you press it, it's going to spray out and you'll hear it. So think about like the air that you can use to like clean off your keyboard or for any kind of spray paint or something. So increasing temperature will increase pressure And then eventually the container will not be able to withstand the pressure. Remember we talked about this before? You can continue to increase pressure until there's no more room between the particles. Okay, you can squish them as close as, they're only so close you can squish them. But the other thing is it's limited by the container. So if you're using a plastic container, it's just going to crack. It's not going to withstand the pressure. But if you're using a metal one, like in most aerosol spray cans, it still does have limits. So eventually that pressure increases too much and the can will explode. Okay? All right, so now we're going to get to actual gas law problems. So the volume of a gas is 250 liters at STP. If the pressure of the gas is held constant and the temperature is changed to negative 25 degrees Celsius, the final temperature of the gas, the final volume of the gas in liters will be equal to. Now do you see this one? This one is often asked on the exam where you're just showing the correct setup and you don't actually have to solve it. All right, so my formula for this is the combined gas law formula, which you don't have to memorize. It is right here on your reference table. So I'm going to write it here. P1 V1 over T1 equals P2 V2 over T2. All right. Now what I like to do is just make a list of the variables. So P1 V1 T1, P2 V2 T2. All right, I'm going to need a different paper when I get to the next one. Okay, so P1, well, let's see, let's go through here. A volume of a gas is 250 liters, so that's V1, 250 liters at STP. Okay, so those come right from here, from table A. And then, so this is in Celsius, but remember I'm going to have to eventually convert it into Kelvin. So let's use the correct Kelvin temperature. So 273 Kelvin. And we'll use 1 atmosphere because no other pressure is mentioned, and that's the easier one to use. All right, so if the pressure of the gas is held constant, that means P2 is also 1 atmosphere. And if it's held constant, it actually becomes irrelevant because it's going to be in the same place on both sides, and I don't need to even put it in the formula, which means in my P1 V1 formula, I can cross out P. So I'm just left with this. So let's see, and the temperature changed to negative 25 degrees Celsius. Well, great. It's supposed to be in Kelvin. So I got to use this formula right here, right? So K equals degrees Celsius plus 273. This is negative 25 plus 273. So remember, I said if you think you're going to do it wrong, use a calculator, right? So I have 25 negative 25 plus 273 equals 248. So there's my T2, 248. My V2, well, it says what is the final volume? So that's what I'm trying to find. All right. Okay. So now what? Well, I'm going to set it up like this. V1 is 250. T1 is 273 equals V2, that's what I'm trying to find, so I'm just going to leave it as V2, and T2 is 248. Okay, well, nothing here looks exactly like what I have, right? So let's go to the next step and cross multiply, right? So I'm going to get 250 times 248 equals V2 times 273. Well, nothing matches exactly yet, but you can see what I'm going to need to do. I'm going to need to get V2 by itself. So without doing any of the calculations, that means I'm going to have to divide by 273. So I can already tell, see how these two divide by 273 and these two do not. So these are two wrong answers. And what are the numbers on the top going to be? 250 and 248. 250 and 298. 250, aha. Because remember, this is really over 1. So that number is also on the top. So 250 and 248. There we go. Okay. So now if the Regents question on the exam just asked for the correct numerical setup, this is as far as you need to go. Just plug the numbers into the formula and you don't have to do anything else. But with this multiple choice question, I had to go a little further in order to get to the part where I could choose the correct answer. Okay? All right. So for this next one, it says, so what I'm going to do is just get a little bit of paper right here so I can start it on there. Okay? So I'm just getting a little scrap paper here. All right. So at 25 degrees Celsius, gas in a rigid container cylinder with a movable piston has a volume of 145 milliliters and a pressure of 125 kPa. Then the gas is compressed to a volume of 80 milliliters. What is the new pressure of the gas if the temperature is held at 25 degrees Celsius? So I know I'm using P1 V1 over T1 equals P2 V2 over T2. So I'm going to make my list. P1 V1 T1, P2, V2, T2. All right, so P1, well, so first I get to T1. It's at 25 degrees Celsius. Of course it's in Celsius. So I do K equals degrees Celsius plus 273. So 25 plus 273. And remember, if you think you're going to do it wrong, just do it in the calculator just to be sure. And we get 298. So our T1 is 298 Kelvin, volume of 145 milliliters, and a pressure of 125 kPa. Then the gas is compressed to a volume of 80 milliliters. What is the new pressure? So that's what I'm trying to find. If the temperature is held at 25. Now 25 was 298 Kelvin. So what do you notice? Well, the temperature is the same. So if a value is constant, I can ignore it in the formula because it no longer affects anything. Well, that makes my calculation a lot simpler. So P1 is 125, V1 145 equals P2 is what I'm trying to find, V2 is 80. So let's think for a minute. So I get some logic in here. I'm only comparing pressure and volume, right? And what did I do to the volume? Well, I decreased the volume. So essentially that means I took a container and I made it smaller. So if I decreased the volume, what do you think should happen to the pressure? Well, I suspect the pressure should go up. So when I get an answer, it should be bigger. If it's not, that's a problem. Okay? So what I'm going to do now is I can just multiply these two numbers, 125 times 145, 18125 equals P2 80. Well, I'm solving for P2, that's my variable, how to get it by itself. I'm going to divide both sides of these by 80. And then I'm going to get my answer. So divided by 80 equals. All right, so what was my initial pressure? 125 kPa. Is this answer bigger? Yes, it is. Okay, so this is going to be 226.5625. So P2 is 227 kPa. But if I'm doing correct significant figures, I have to go by this one. This only has 2 significant figures. So if I was rounding to significant figures, if that was required, this is fine for the Regents exam because they're not going to ask you to do significant figures most of the time, and this question did not. But if I had to round it to 2 significant figures, that would be my answer. Because 227 is between 220 and 230 to 2 significant figures, and it is closer to 230. Okay? All right, so now we're going to look at another one. So, well, first of all, 230. See, there we go. I said 227 rounds to 230. There was our answer. All right. So let's look at the next one. A gas occupies a volume of 444 milliliters at 273 Kelvin and 79.0 kilopascals. What is the final Kelvin temperature when the volume of the gas is changed to 1,880 milliliters and the pressure is changed to 38.7 kPa? Well, this one I got a lot going on, right? So we use the same formula. Okay. P1 V1 over T1 equals P2 V2 over T2. Make my list of variables. P1 V1 T1, P2 V2 T2. Volume of 444 milliliters, 273 Kelvin, 79.0 kPa. What is the final Kelvin temperature when the volume of the gas is changed to 1880 milliliters and the pressure is changed to 38.7 kPa? All right, so let's see what's happening here. What is happening to pressure? Pressure is decreasing, okay? And volume is increasing. So I'm going to try and guess what happens to temperature. Okay, well, if you look, the one that deals with pressure is either volume and volume and pressure both deal with temperature, right? So, and they're both direct. So what that means is if the pressure is decreasing, I suspect the temperature to decrease. If the volume is increasing, I expect the temperature to increase. So these are kind of opposing factors, so it's going to be interesting to see how that comes out. So let's plug in our numbers. P1, 79.0, V1, 444, over T1, 273, equals P2, 38.7, V2, 1880, over T2. Well, that's what I'm trying to find. Okay, so what did I tell you? Every single time we're going to cross multiply. So I'm going to get 79.0 times 444 times T2 equals 38.7 times 1880 times 273. Okay, how do I solve this? Well, I could multiply these numbers out first. So just do 38.7 times 1880 times 273, and then do 79 times 444. Or what I like to do is just realize that I need to get rid of this. I need T2 by itself, right? I need T2 by itself. So I need to get rid of the 79.0 and the 444. So if I divide them like this, now I have T2 by itself on that side. That's beautiful. But if I do that on this side, I need to do it also on this side. So 79.0 and 444. Now I definitely need to use my calculator. Okay, so I'm going to do, watch how I do this. 38.7 times 1880 times 273. I just like to press equal in between. I got to the end of that line. Now I'm going to do divided by 79.0 equals divided by 444 equals. All right. So T2 is 566.267. Keep going. Well, all of these have three significant figures, so let's go to that. 566K. Hopefully I have an answer That is 566K because this was multiple choice. And look, I do right there. Okay. All right, so now let's try another one. It's all about practice, okay? So let's set it up because I'm telling you, normally on the exam, you have to figure out that you need this formula, but we are just doing a whole bunch of the same formula, right? So here, and then I need a list of variables. Okay, so the volume of a sample of gas at 273 Celsius. Okay, well, it's 273 Celsius. I know right here, to change Celsius into Kelvin, I got to plug Celsius in here. So it's actually going to be 273 plus 273, which equals 546 Kelvin, 200 liters. If the volume is decreased to 100 liters, what is the new temperature be? Well, it didn't even talk about pressure, so get rid of it. Okay, so get rid of it in the formula. So I have V1 over T1 equals V2 over T2. Cross multiply. 200 times T2 equals 546 times 100. So that's 200 times T2 equals 54600, and multiply those together. To get T2 by itself, I have to divide by 200, which means I need to do that on both sides. So let's just see that 54600 divided by 200 equals 273 Kelvin. Is that one of my answers? You betcha it is. So why does this make sense? If I took the volume and cut it in half, the temperature is going to be cut in half because they're directly related. So when the volume decreases, the temperature decreases. All right. Okay, let's keep moving. All right, here we go. Let's do another one. Okay, so the bonus, you know, we're using the same formula. You don't get this luxury on the exam, but in this case you do. So P1, V1, T1, P2, V2, T2. All right, here we go. Let's read it. A sample of gas has a volume of 2 liters, a pressure of 1 atmosphere. When the volume is increased to 4 liters at constant temperature, constant, get rid of it, constant. All right, what the pressure will be, so I'm trying to find this. So P1 is 1, V1 is 2, P2 I'm trying to find, times V2, which is 4. So this is 2 equals P2 times 4. I divide by 4 to get P2 by itself. 0.5 equals P2. So I have something that says that, an answer choice? You betcha, right here, C. Okay, let's get another piece so that we can, you do have some space in this one, but I don't think it's enough space to do what I've been doing here. All right, same formula, P1 V1 over T1 equals P2 V2 over T2. Okay. So P1, V1, T1, P2, V2, T2 has a volume of 2.00 liters, 323 Kelvin, 3.00 atm. What will the new volume be if the temperature is changed to 273 and the pressure is changed to 1 atmosphere? So do I have anything that's constant? No, I do not. So I got to keep it all. All right, so let's plug it in. 3 for P1, V1, 2. I'm going to leave off these because 3.00 is the same as just for multiplying purposes, just 3. And 2.00 for multiplying purposes is just 2. So I'm just going to simplify it like that. Over 323 equals P2 is just 1. V2 is what I'm trying to find, and T2 is 273. All right, so what did I tell you we're going to do? We're going to cross multiply every time. So 3 times 2 times 273 equals 323 times 1 times V2. Now I'm going to do this one the other way. So instead of worrying about am I dividing or multiplying, I'm going to multiply these numbers together. So I'm going to do 3 times 2 times 273 equals 1638. And I'm going to remember not to round at this point. I'm going to write exactly what the calculator tells me. 323 times 1 is just 323. Okay. In order to get V2 by itself, I'm going to divide both sides by 323. Okay, I still have this right here, so divide it by 323 equals, all right, so my answer for V2 is 5.0712074. Keep going. All right, so let's look back at our numbers. Well, they mostly look like they have 3 significant figures, so let's round this to 3. 5.07. And what were my units? Liters. Okay. So does this make sense? Well, I increased the pressure. I decreased the pressure, right? So that should make volume go bigger. And I also decreased the temperature, which should make the volume get smaller. But the effect of the pressure must have been much greater, right? A much greater difference from 3 down to 1. Okay, so at least I have a reasonable number. If I get an answer of like 6,000 liters, that probably seems a little bit suspect. Okay, so 5.07 liters. So for this one, I have to write my answer on the line, not forgetting the unit, because remember, no naked numbers. Okay, all right, let's keep moving. We got 4 left. Okay, so let's clear this calculator. P1 V1 over T1 equals P2 V2 over T2. P1 V1 T1 P2 V2 T2. It seems silly, but trust me, if you do it this way, you will make far less mistakes, so you'll be thankful in the long run. A gas at STP. Okay, so STP, remember, where do I find it? On the reference table, but here's formulas, here's STP. Now if you have a choice, you could use the easier one, but if I look here at this problem and I scan, I don't see any other pressure or temperature mentioned, so I'm just going to say the volume was 1.00 liters, so pressure, we're going to use 1 atmosphere, and temperature is 273 Kelvin. So these two values came from STP, not from my problem, but it told me that it was at STP. If the pressure is doubled, okay, so I was at 1 atmosphere, double it, you get 2 atmospheres, and the temperature remains constant. So the temperature stays at 273. As soon as they tell you something is constant, what should you do? Get rid of it from the equation. Make your life easier. Okay? What is the new volume? Okay? So this is actually an easy problem. Pressure 1 is 1, volume 1 is 1, pressure 2 is 2. Alright, so the 1 times 1 is what? 1. 2 times V2. How do I get V2 by itself? Divide it by 2. So 1/2. We don't write that as a fraction though. 0.5. And what units did I use for volume? Liters. Now let's make sure it makes sense. My pressure increased from 1 to 2, so my volume should decrease. Did it? You betcha. So it is going to be 0.5 liters. Okay. Just a couple left. All right. A 2.5 liter sample. All right. First, I guess I should write it. P1 V1 over T1. P2 V2 over T2. Okay, make my list of variables. P1, V1, T1, P2, V2, T2. A 2.5 liter, there's the volume. Sample of gas is at STP. Okay, so 1 atmosphere, 273 Kelvin. Because I'm scanned real quick and I didn't see kPa mentioned, so I'm going to use the easier pressure. When the temperature is raised to 373 degrees Celsius, but remember, it's K equals degrees Celsius plus 273. So I got to plug 373 in there and do 373 plus 273. So 373 plus 273 equals 646. So that is my temperature. And the pressure remains constant, so it stays at 1 atmosphere. But remember, as soon as something is constant, you can remove it from the equation because it's not going to affect anything because it's on both sides. It's like dividing by the same thing or multiplying by the same thing. We're just doing that to solve. We don't need to do it here. So volume is what I'm trying to find. So let's plug them in. V1, 2.5. T1, 273 equals V2 trying to find T2, 646. Let's look at what we think should happen. We don't know what's happening to the volume, but we know the temperature is increasing. So what should happen to the volume? I suspect the volume should increase, right? When the temperature increases, volume increases. If I don't get a number like that, I should be concerned. So remember, we're going to cross multiply. So 2.5 times 646 equals 273 times V2. All right. So I could multiply this right now. I have 646 here times 2.5 equals 1615 equals 273 times V2. In order to get V2 by itself, I got to divide both sides by 273. So take this, divided by 273 equals 5.915759, blah, blah, blah. And what were my units for volume? Liters. So what did I say should happen? If I increase the temperature, the volume should increase. Did it? You betcha. If I look at here, I have some numbers with 3 and some numbers with 2 significant figures. Unless they mention it, you don't have to worry too much about it. So it's going to be 5.9 liters. 5.9 liters. All right, 2 left. Are you ready? We can do it. All right. The volume of a gas at 500 Kelvin. All right, so let me start this. P1, V1 over T1. So you see how I'm writing it every time? I know it seems silly, but you're going to remember it better if you are writing it every time. So P1, V1 over T1 equals P2, V2 over T2. Make your list of variables. P1, V1, T1, P2, V2, T2. All right, now we look at the problem, okay? And it says the volume of a gas at 500 Kelvin is 50.6 liters. Calculate the volume, so that's what I'm trying to find, at 750 Kelvin. Okay, guess what? Question didn't even mention pressure. So I can eliminate pressure from both the question and the equation. Then I'm going to plug in my numbers. V1, 50.6. T1, 500 equals V2 over 750. Okay, then we are going to cross multiply. 50.6 times 750 equals 500 V2. Okay, times V2. But all right, so let's see, what do we get? 50.6 times 750 equals 37,950 equals 500 times V2. How do we get V2 by itself? Well, we divide both sides by 500. So I take this number, divided by 500. What do I get? 75.9 equals V2. And I was in liters. Now let's see if that makes sense. What happened to my temperature? It increased. When temperature increases, volume should also increase, and it did. 75.9 liters. All right. Whew. One more. A 1.5 liter sample of gas. Okay, so every single time, what we need to do, P1 V1 over T1 equals P2 V2 over T2. Make your list of variables. P1 V1 T1 P2 V2 T2. Start plugging in your numbers. Volume 1.5 liters, 150 kPa, 250 Kelvin is changed to STP. What is the new volume? So if it's changed to STP, that means I know the temperature, 273 Kelvin. Now which pressure? Well, you see this is in kPa, so that means I want the kPa part of STP. So 101.3 kPa. All right, let's plug our numbers in. Nothing is constant, so that means I got to use the whole formula. So P1, 150, T1, V1, sorry, 1.5, T1, 250 equals P2, 101.3, V2, well, trying to find it, and T2, 273. All right, so what did I tell you every single time? Cross multiply, right? So 150 times 1.5 times 273 equals 250 times 101.3 times V2. All right, now last time I moved both of these underneath, but what I'm going to do this time is show you how you might make less mistakes if you do the multiplication on each side. So I'm going to just take these three numbers and multiply them. 150 times 1.5 times 273 equals 61,425 equals, and then on this side I'm going to do these two numbers and multiply them together. 250 times 101.3, 25,325 times V2. Okay, so now I have these two. So what do? Well, I divide both sides by 25,325. 25,325. So let's do it. 61,425 divided by 25,325 equals 2.425. So 2.425468. Now, keep going for a long time. Was I finding V2? That should be in liters. Okay, so you know what, my answer is, makes sense. It's not too far off from this. My pressure did get slightly less, so I do expect my volume to go up, and my temperature did increase, so I do expect my volume to go up. So both were pushing for the volume to go up, which it did. Okay, so I'm going to round this. If I look at mine, I do have this one, which is two significant figures, so I'm going to round it to 2.4, and what was I finding? Liters. And there we go. That's it. So important things to remember about the combined gas law. Writing the list of variables, P1, V1, T1, P2, V2, T2. Super important, right? Remembering STP, where to find their values. Okay. Remembering that temperature has to be in Kelvin. So you're going to need to use this conversion. Remember, the formula is here. If you forget about what something is a unit for, you're like, I don't remember. Okay, so it's going to be, here's a unit for pressure. You also can see that atmospheres is a pressure unit, and sometimes it even says it in the question. Here we have temperature, and down here we have volume. So use the information that you have, right? And then that's it. So hopefully that helped and you understand it a little better.